the heart of all calculations in electrochemistry revolves around the standard reduction potentials of the different redox reactions. So that's what this video is going to go over. Now this table here gives the standard reduction potentials of a number of common redox reactions that you would see. A couple things to notice on the table. That over there is the standard reduction potential. Something that has a high standard reduction potential wants to be reduced. So fluorine, right, F2 plus 2 electrons give 2F minus, that wants to be reduced, that reaction wants to happen. Notice all the way at the bottom, lithium plus an electron to give lithium solid, that has a negative 3.04 standard reduction potential. That reaction does not want to happen. Now, what confuses people sometimes is that all of these are written as reduction potentials. But in a redox reaction, you have both a reduction reaction and an oxidation reaction. So what do you do when you're calculating? So we can go over that now. So I want to use the same reaction that we used for the video on the voltaic cells. Zinc solid plus copper 2 plus to give me zinc 2 plus copper. So E cell, that's the cell potential, right? E cell is going to be equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode. So this is a really important equation right here. So you have to figure out what is happening at the cathode, what's happening at the anode. So if you remember from the voltaic cell, the cathode is the site of reduction. The consonants go together. So cathode reduction. That means our cathode is copper 2 plus 2 electrons to give me copper. Our anode then, the site of oxidation, is going to be zinc solid, gives me zinc 2 plus 2 electrons. So when I'm solving for E cell then, for this example, E cell will equal the standard reduction potential at the cathode. So copper 2 plus 2 electrons to give copper solid. That's right there. So 0.34. So it's going to equal 0.34 volts minus zinc 2 plus 2 electrons to give me zinc. I'm not flipping the sign here, because by subtracting the anode from the cathode, I'm subtracting a negative, which means overall I'm going to get positive 1.10 volts. So that's something that confuses students sometimes, is they flip the sign because the reaction that's happening is an oxidation reaction, not a reduction reaction. You don't flip the sign when you're using this equation, because you're calculating the E cell from the reduction potentials only. What you can do, and if you find this easier, you can do it. Another way to calculate E cell. Instead, I'm going to say, okay, E cell is going to equal the standard reduction potential at the cathode, so 0.34 volts, plus the standard oxidation potential, you could call it. In that case, you're adding here, and then you flip the sign, so 0.76 volts to give you 1.10 volts. That's another way you can do it. But if you flip the sign, you have to remember you're adding the two of them together. You're not subtracting the one from the other. Now, in general, you're going to want your E cell to be positive. That means it's going to happen likely. If it's negative, it's not really going to happen. You'd have to put in a lot of external current to get that to happen. So generally, when you're checking your answer, if you have a positive cell potential, that's usually a good thing. Now, one more important note I want to make. Stoichiometry does not affect cell potential. So if I have silver plus 1 electron to give me solid silver, my standard reduction potential is 0.80 volts. If I have 6 silver plus 6 electrons to give me 6 silver solid, my standard reduction potential is still 0.80 volts. It doesn't change. When you calculate, enthalpy and other values, you would multiply by whatever the coefficient was. You don't do that in standard reduction potential. It's constant no matter the stoichiometry.